3.1 is extrema on an interval. Here's the good news. Having come off of chapter 2, which is really deep in like derivatives and all of the complications that can persist as a result of them, you're going to find that chapter 3's derivatives are very clean, very simple, very straightforward. It's kind of like when you're really young and you're learning how to do long division, right? Like really long division, you know, like a 4-digit divided by a 3-digit kind of thing, or like a 6-digit divided by a 3-digit kind of thing. I might be having a child do this right now. And you're like, oh my word, is this ever going to end? And the reality is yes, because eventually you've got the whole idea of division down, right? And so we don't need to keep doing the complicated divisions, and then eventually you're allowed to use a calculator for those as well. This is like that, where you get to the point where you're like, okay, now I really know my derivatives, which was the point. We wanted you to really know your derivatives. And this chapter's focus is on applying what you know, but the derivatives themselves are going to be much more straightforward. All right, so extrema. Let's talk about the definition of extrema. We're going to have a function f. I'll draw pictures in a minute. It's defined on an interval I containing c. F of c is the maximum of f on the interval I when f of c is less than or equal to f of x for all x and I. And it's the minimum when f of c is greater than f of x for all x and I. Extrema means maximum and minimum. Yes?
Minimum and maximum are the other way around.
Oh, do I have them backward on there? Say that again, Josh.
Like the minimum was the first one where f of c is less than f of x.
Yes.
Maximum.
Oh, did I just say it wrong when I was reading it out loud?
Yeah,
Oh, I'm so sorry.
Minimum.
I'm sorry. That's because I have terrible vision. Okay, the first one, it's written correctly. I'm like reading it. Like it is written correctly. Okay, thank you for helping me clarify. I appreciate it. The first one is the description of minimum. The second one is the description of maximum. So sorry. Yeah, f of c is the minimum when f of c is less than or equal to f of x, and f of c is the maximum when f of c is greater than or equal to f of x. Okay. Maximum and minimum are extrema. So when we hear the word extrema, we want to think maximum, minimum. So the maximum and minimum values on the interval are the extreme values, or extrema, of the function on the interval. We also sometimes call them absolute maximum or absolute minimum, or global maximum and global minimum. So I'm going to draw a picture that you can set on the side of your descriptions as well. So it has to be a closed interval for us to have this discussion, right? Closed means the interval is trapped on the endpoints. It doesn't continue infinitely on each side. This point right here, since I listed it first, would be my absolute minimum. And this point, up here would be my absolute maximum. Okay, so a little context. If you talked about absolute maximum and minimum with discrete values, right, not a graph, we could have everybody in this classroom stand up, right, and we could actually find among all 12 of us the absolute tallest person, right, and it could be 2 people. I mean, it doesn't have to be just one. There could be 2 locations that are the absolute maximums on this graph, or 2 that are the absolute minimums. That's a possibility as well, or more than that. But we could also find the absolute shortest person, right, the absolute minimum height in this classroom, right? So it doesn't have to be done with a continuous kind of a graph. It can be done with a discrete collection of objects as well, the maximum and the minimum ideas. The extreme value theorem actually tells us that if we have a closed interval, like I mentioned before, then we absolutely will have an absolute max and an absolute min. There's no way to not have one. Right? If you talked about this group of people, we have a finite number of people. There is a maximum height and there is a minimum height. It exists. Now, relative extrema may or may not exist. Relative or local extrema says if there is an open interval containing C on which f of C is a maximum or a minimum, then you can say that f has a relative maximum or a relative minimum at that location. So this one does not need to be close-ended. It can have infinite sort of boundaries that continue on forever. So if I'm drawing this picture, I can draw something like this to give us an idea. We've seen a graph like this once before. The graph continues on. Obviously, eventually this graph will go down past my lowest point that's on this picture, right? And it will go up if the arrow continues going up on the other side. But this one right here is what we would call a relative minimum value. And this one is a relative maximum value. And what it really means is that there's some sort of area around here where it's the smallest, right? And there's some sort of area around here where it's the biggest. So with the exception of my husband, my son, who lives in my house right now, that one, is the tallest by a smidge of all my children in the house right now. But he likes to do this when he comes and gives me a hug. He stands up really tall because he likes to feel like he's towering over me. It's the funniest thing. It's actually kind of irritating. But he feels like that he's the tallest, right? And because in that local, that relative area, that small group of people, he is the tallest. Okay, it's all relative, right? I can tell you that I'm short, and I am fairly short, but only compared to people who are taller than me, right? You put me in my Sunday school class with the 9 and 10-year-olds, and I am tall. But it's all relative, right? It's the grouping that we're talking about. So when we're talking about relative extrema, we're talking about nearby values. Is it nearby the biggest value or the smallest value? Okay, so critical numbers are numbers where the derivative is equal to 0. Or it doesn't exist. So anytime we have a location where we have a peak or a valley, where it's a nice smooth peak, this would be the derivative 0. This is a location where f prime of c is 0. If this is c, that is to say, right? If this is the value c, right, on a graph. Or if we have a location where there is a sharp turn, a hole in the graph, right? Those are places where the derivative doesn't exist. This would be a location where f prime of c does not exist. We'll put D and E. But if you look at it, do you see how that still makes it look like in both of these cases that it's a relative maximum? Right? In the nearby area, in fact, the graph as drawn almost looks like it doesn't continue on the endpoints. You could even say it's an absolute maximum on this particular graph's pieces that I've drawn. Okay, so these locations where there have these peaks and valleys occur in one of two ways. Either the derivative is 0 or the derivative doesn't exist, are locations where I have, or potentially at least have, relative extreme points. So that's what the second theorem here says. If we have a relative minimum or a maximum at x equals c, then we call c a critical number of f. So we need some guidelines about how we go about finding extrema, and that's what we're going to do for the rest of this material in this section. So these are our four guidelines for finding relative extrema, extrema in general. So to find the extrema of a continuous function f on the interval ab, we need to first find the critical numbers. So this piece where it says find the critical numbers is equivalent to telling you find where f prime of x is 0 and where f prime of x does not exist. That's what step 1 is. I take derivatives, I set them equal to 0, or I look at places where they can't actually equal anything, right? The derivative doesn't exist, and I find out those numbers. Step 2 is that I evaluate them at those values. Right? So I find out, oh, it happens at x equals 5. Okay, well, what's the y value there? Oh, it happens at x equals negative 3/4. Okay, what's the y value there? So step 2 is find the corresponding y value, or f of x value. Step 3 is looking at endpoints. So I promise I'm going to come back to this screen, but I want to go back and look at a picture I drew earlier. This picture happened to have a relative extrema down here that is the absolute minimum, right? And the endpoint was the absolute maximum. Yeah? So endpoints are another location where we can have extreme values, and that's what we're doing on step 3, is we're evaluating the endpoints. And so you're going to have a collection of values. Maybe you just have 2 values. If you have 2 values, it's easy. The biggest one's the max, the smallest one's the min. But maybe you have 6 or 7 values. So however many values you have when you get to step 4, you simply look for the biggest y value. That's your maximum value. You look at your biggest or your smallest y value. That's the minimum value. So step 4 is just observing the data that you have and making a declaration. Ah, this is my one. This is it. Okay, so a bit of warning. When I ask people to find extrema, they usually remember to do one of the 2 things here. They'll either remember to do all the relative stuff, or they remember to do endpoints. But oftentimes they don't remember to do both. You have to consider both types of values. The relative points, derivatives equal to 0 and does not exist, and the endpoints. Both must be considered to make the decision. So, let's take a look at one. I told you the derivatives are going to get much easier, right? Do you like this one? Me too. Okay, so step 1 is finding where the derivatives, so I'm gonna write down my steps on this one. I'm not normally going to do that, but just to show you that we're doing all of them. Step number 1 is to take the derivative and set it equal to 0. So what is the derivative of this function?
3x squared minus 6x.
3x squared, minus 6x. Everybody good with that? Okay, this is a polynomial, so it can equal 0, but it can't equal does not exist, right? Does not exist happens potentially for radicals. It can happen for functions that have denominators, right? Like something in a denominator. It can happen with our rational exponents that form radicals, like a power of 1/3 would be the same as a radical, right? So those are the kinds of places where you have to worry about that does not exist. Polynomials don't have that, so it's just equal to 0. So how do we find out where this is equal to 0? There's a couple of ways. I'm going to factor. If you don't want to factor this one, it's okay. There's another option. You can just simply shift things around. You just need to be careful when you do that you don't lose anything. So if we factor, there's a 3 and an x involved in both pieces. If I take 3x out, I've got an x left and a minus 2. Is everybody good with my factoring? Okay. If we set each piece equal to 0, then with the first one gives me x equal to 0, and then the second piece gives me x equals 2. Okay? And the directions here simply said to find critical numbers, so we would be finished at this point. Step 1 is exactly what this question is asking. If I was asked to go further, right, actually find the extreme values, I would actually have to evaluate each of these points, 0 and 2, in the original function. That'd be step 2. Then I'd have to consider endpoints, which I wasn't given any here because the directions didn't require it, right? And I'd look at endpoints, and then I'd examine all the different values. This one simply said find critical numbers. These are them. The next one has the full, fleshed out process. Let's look at that one. Okay, still, this is not so bad. And in particular, I've chosen a function that you're familiar with. What is this a graph of? Somebody said it. Somebody whispered it. What's a graph of?
Parabola.
It's parabola. It's parabola opening how? Up or down?
Down.
Parabola opening down. So there's going to be a peak, right? Because a parabola opening down will have a peak on it. And then we have to consider the endpoints potentially as well, right? Those are the 3 options that we would have here. So we start out the same way we did in the last one. Number 1, critical numbers, derivative equal to 0. So what is the derivative of negative x squared plus 3x minus 5?
Negative 2x plus 3.
Negative 2x plus 3. Fantastic. And then what do?
We set it equal to 0.
Yep, critical numbers sets it equal to 0. This one there's no factoring because it's actually a linear equation. If I solve this, what does x equal? 3 over 2. Or if you want to write it as in a decimal form, you can. So you can write it as 1.5, doesn't matter. So your preference. Okay. Okay, this is step one. We found the critical number. There is only one. And we know that this is going to be a vertex of a parabola because we know some math, right? This is familiar kind of a shape for us. They're not all going to be familiar to you, but this one is. So step two would be finding the y value at that point. So we're going to find f of, I'll write it as a decimal this time, 1.5. So we take the original equation, which was negative x squared, so negative 1.5 squared. Remember, the negative's not being squared, the 1.5 is. Plus 3 times 1.5 minus 5. Now, if you don't want to show me the plugging in the 1.5, that's fine. You don't have to do that, but that's what we're doing. We're figuring out what is f of 1.5. All right, so grab a calculator if you wish. Do it by hand or in your head, whatever it takes. What do you get when you put 1.5 or 3/2 into this equation? We'll do it in decimal form since I put decimals down here. Do you have one, Dylan? Did you get one, a value for this? Yep, negative 2.75. Okay, does everybody have negative 2.75? Okay, so that was step two. Step three is to test the end points. So the end points that we are given are right up here, negative 2 and positive 1. So I want to find f of negative 2 and f of positive 1. And somewhere along the way, I need to make sure that the y, or the, actually, I'll mention it in a minute. Let's just do this for now. Okay, what is f of negative 2? I'll mention that in a minute. Hold tight to that thought, Josh. It's okay. I'm going to address it. What happens if I put negative 2 into the equation? I'm not asking a hard question. I'm saying put in negative 2 and evaluate it. Y'all can do this. What do you get?
Negative 7.
Okay, negative something. I don't have negative 7. I have something different, but I could be wrong on my paper too. What do y'all get? I don't have a calculator. Negative 15, that's what I have written down. Is that okay? All right, negative 15. And then we want to put in 1. Okay, so what is 1 plugged in? Negative 3. Okay, so these are the 3 points to consider, right? Critical points and the end points. There's a catch, though, and I feel like just by seeing what Josh said that he saw the catch. Do you see the problem, Josh? There's a problem with this particular point.
It's higher.
Then what? Then,
It's not in between negative 15 and negative 3.
right, it's not on my interval. Do you guys see that? There is the critical point. It exists, but it's not in between the endpoints I'm looking at. It's something like we have this, right? We have a parabola, yay, like this, but my endpoints start and stop here. So yeah, there's a point over here that's a maximum value or a minimum value or whatever, but it's not within the interval I'm looking at. I'm only supposed to be looking in here. So this is on purpose that I've put this in here because it happens on at least 1 or 2 of the problems that you're working with, where they're going to find a value, or maybe you're going to find 2 or 3 values, but they're not all inside of the interval that you're working with. So what that means is that even though, let me shift that up, even though this may be the smallest or the biggest value, it doesn't happen to be here, or it is the smallest value here, right? Yeah, the biggest value here. It is the biggest value here. It doesn't matter. It doesn't answer the question that I'm being posed. So this one is outside my interval. It's outside the interval that I was given, which was negative 2 to 1. So it means I can't consider it as an answer because it's not on my interval. So these are my two values, negative 15 and negative 3. Which one is the smallest? Negative 15. So this is my absolute minimum. My absolute minimum is negative 15, and it is at x equals negative 2. And my absolute maximum would be the other one, negative 3, at x equal 1. This is one way to write your answers, perfectly acceptable. There's another way you can write this too. You could say that we have an absolute maximum, and you could write it in ordered pair notation. At the ordered pair, negative 2, negative 15. And we have, sorry, was that minimum? That was minimum. We'll move that. Absolute minimum there. And we have absolute maximum at 1, negative 3. That's an alternate way to write it. It doesn't matter to me which one you do, but whichever one makes sense or you like better is fine. Okay, does that make sense? So be paying attention to those details. Okay. We'll do one more. It'll go quickly. We need to find the derivative. So our derivative, actually I'm not going to write all the steps out anymore, but we're going to find h prime of t. So this is a quotient rule. So it's low d high. So low d high minus high d low all over low low, like so. If I simplify, I have t minus 2 minus t over t minus 2 squared. The t's cancel, so I have negative 2 over t minus 2 squared. This can't equal 0. Why?
Because of the square.
It's not because of the squared. That's a good guess. Because why? The t's on the bottom, and specifically it's only on the bottom. Yeah, there's no variable on the top. Only if the top is equal to 0 can the fraction equal 0. And there's nothing on the top that can do that because it's a constant, so it can't be 0. It can equal does not exist. Where would this derivative not exist? At t equal to 2. And that's actually really not bad because look at my interval. It doesn't include that value, right? What's happening at t equal to 2? Do y'all know from this graph? You should, because we've talked about it in this class. There's a vertical asymptote there, right? So if there's a vertical asymptote, I'm not going to get a value ever. I don't care how many derivatives I take. There's no value going to happen from that. So what that means is that there are no critical values. So our second step then is to consider the endpoints. So I'll jump to the chase on this one. We're going to get h of 3 and h of 5. If we put those in, I'm just going to let you know what they are. The first one's 3. The second one's 5/3. 3 is bigger, right? This is my maximum. This is my minimum. And we would write them as such. So we have an absolute max. I'll put the intervals or in a point notation at 3, 3. And the absolute min at 5 and 5/3. Okay, I'm going to stop right here on this. I'm going to go back to my office and I'm going to record the last problem. There's one more question over here. It'll take me like probably 3 minutes to record it. So go in, watch the last 3 minutes of this so that we can stay on target for finishing this section since we took so long to review the test. So do that, and then your homework, group work, not group work, your web assigned work stuff will be due next class period, okay? All right, as promised, our last example. This one involves trig, and it actually involves trig from a very concrete standpoint, like where it's not just trig inside of calculus. Like we need to remember some of our trig in this section. So if you are a bit rusty on that. This section, or this problem is probably not going to be your favorite, but it's a good one to remind you how to think about these. All right, so we're finding the same pieces of information, the absolute value, the absolute extrema on an interval. So we take our derivative. So the derivative of cosine is negative sine, so this is -3 sine of x. This is on the interval 0 to 2 pi, and that's often the case when we're doing these with trig, is that they'll often use either 0 to 2 pi or 0 to pi. It could be that they're using like pi halves to 3 pi halves, those kinds of things too. So just be aware that the intervals are usually fairly small, and they're corresponding to unit circle type values often. All right, so we're going to set this equal to 0. A sine function, just like our polynomial functions, don't have any places where they don't exist. Sine functions are nice and smooth and they go like this, they wave, right? So this will equal to 0 from the unit circle at the values of 0 and pi. And let me remind you on the unit circle, because I know that it's been a while. Even if it's just over spring break, it's been a while, right? So here's my, my unit circle values. And if I'm going from 0 to 2 pi, it means I'm going all the way around the circle like this. The sine values are the y values. And so my y value is 0 here, and my y value is 0 here. This corresponds to an angle of 0, and if I go all the way over here, it corresponds to an angle of pi. So the sine values are 0 at 0 and pi. The -3 part here doesn't affect the sine values. So I'm going to test these 2 points. So I want g of 0, and I want g of pi. Okay, so this is step 2. Step 2 is identifying the corresponding y values. So I really want 3, and it's the original function, so 3 cosine of 0. And at this point, you can actually put that in your calculator if you wanted to, or you could go back to your unit circle and recognize that the cosine of 0 is 1, so 3 times the 1 would be 3. And I want 3 cosine of pi. And the cosine of pi is -1, so this is 3 times -1, or -3. Okay, so I'm gonna label these because this is a very nice one to see the pieces that we're doing. So this is step 2. Step 3 is my end points. So I test the end points. Well, the end points are 0, what I already tested, but I'll write it in just for good measure here. And the other end point is 2 pi. So again, if I do 3 cosine of 0, and you don't have to write it a second time, but I'll do it this time only, I get 3. And the other one is actually 3 cosine of 2 pi. Now, the kicker with unit circle values, right, is that 2 pi just goes all the way back around to where you are. So the 2 pi values are the same as the 0 values. So this is just another 3, right? So considering all of these values, these 3 are all maximums. Yeah, so we can write down, I'll write this in the other notation this time, not the ordered pair notation. This is an absolute max. Hang on, I didn't write absolute, so just for clarity, I'll put that in there. This is an absolute max of 3, and it happens at 3 values at x equals 0. Well, 2 values, and 2 pi, because one of them is repeated. Right, this is a repeat. So I have 2 places where the absolute maximum occurs. And the absolute minimum is going to be -3, and this happens at x equal pi. And if you think about my, sort of wavy function up here, you can see why this is happening, right? The minimums just keep happening over and over and over again, and the maximums as well, over and over and over again. And so what's happened is we have restricted our view to something that goes from like here to here. So you see 2 maximum values, right, here, and you see 1 minimum value on that interval. So just depending on how big the interval is will depend on how many times you see that repeated maximum or minimum value.